about generic types, traits, and lifetime. Every programming language has tools for effectively handling the duplication of code of concepts. In Rust, one such tool is generic abstract standards for concrete types or other properties. We can express the behavior of generics or how they relate to other generics without knowing what will be in their place when compiling and running the code. Functions can take parameters of some generic type instead of a concrete type like i32 or string. In the same way, a function can takes parameter with unknown values to run the same code on multiple concrete values. In fact, we have already used generics in chapter 6 with option T, chapter 8 with vector T and hash map key V, and chapter 9 with result T. In this chapter, you will explore how to define your own types, functions, and methods with generic. First, we will review how to extract a function to reduce code duplication. We will then use the same technique to make a generic function from the two functions that differ only in the types of their parameters. We will also explain how to use generic types in struct and enum definitions. Then you will learn how to use traits to define behavior in a generic way. You can combine traits with generic types to constrain a generic type to accept only those types that have a particular behavior as opposed to just any type. Finally, we will discuss lifetimes, a variety of generics that give the compiler information about how reference related to each other. Lifetime allow us to give the compiler enough information about borrowed values so that it can ensure references will be valid in more situations than it could without our help. Removing duplication by extracting a function. Generics allow us to replace specific types with a placeholder that represents multiple types to remove code duplication. Before diving into generic syntax, then first look at how to remove duplication in a way that doesn't involve generic types by extracting a function that replaces specific value with a placeholder that represents multiple value. Then we will apply the same technique to extract a generic function by looking at how to recognize duplicated code you can extract into a function. You will start to recognize duplicated code that can use generic. We begin with the short program and listing 10-1 that finds the largest number in a list. We store a list of integers in the variable number list and places a reference to the first number in the list in a variable named largest. We then iterate through all the numbers in the list, and if the current number is greater than the number stored in largest, replace the reference in that variable. However, if the current number is less than or equal to the largest number seen so far, the variable doesn't change and the code moves on to the next number in the list. After considering all numbers in the list, largest should refer to the largest number, which is in case is 100. We have now been tasked with finding the largest number in two different lists of numbers. To do so, we can choose to duplicate the code in listing 10-1 and use the same logic at two different places in the program as shown in listing 10-2. Although this code works, duplicating code is tedious and error prone. We have to remember to update the code in multiple places when we want to change it. To eliminate duplication, we will create an abstraction by defining a function that operates on any list of integer passed in a parameter. This solution makes our code clearer. Let us express the concept of finding the largest number in a list abstractly. In listing 10-3, we extract the code that finds the largest number into a function named largest. Then we call the function to find the largest number into two lists from listing 10-2. We could also use the function on any other list of i32 values we might have in the future. The largest function has a parameter called list which represents any concrete slice of i32 values we might pass into the function. As a result, when we call the function, the code runs on the specific values that we pass in. In summary, here are the steps we took to change the code from listing 10-2 to listing 10-3. Identify duplicate code, extract the duplicate code into the body of the function and specify the input and return values of that code in the function signature. Update the two instances of duplicated code to call the function instead. Next, we will use the same steps with generics to reduce code duplication in the same way that the function body can operate on an abstract list instead of specific values. Generics allow code to operate on abstract types. For example, we say we have two functions, one that finds the largest in a slice of i32 values and one that finds the largest item in a slice of char values. How would we eliminate the duplication? Let's find out. Generic data types, we use generic to create definition for items like function signature or structs, which we can then use with many different concrete data types. Let's first look at how to define function structs, enums and methods using generics. Then we will discuss how generics affect code performance in function definition. When defining a function that uses generic, we place the generics in the signature of the function, where we would usually specify the data types of the parameters and return value. Doing so makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function listing, 10-4 shows two functions that both find the largest value in a slice. We will then combine this into a single function that uses generics. The largest i32 function is the one we extracted in listing 10-3 that finds the largest i32 in a slice. The largest car function finds the largest char in a slice. The function bodies have the same code, so let's eliminate the duplication by introducing a generic type parameter in a single function. To parameterize the types in a new single function, we need to make the type parameter just as we do for the value parameter to a function. You can use any identifier as a type parameter name, but we will use t because by convention type parameter name in Rust are short, often just a letter, and Rust type naming convention is camel case short for type. T is the default choice of most Rust programmer. When we use a parameter in the body of the function, we have to declare the parameter name in the signature so the compiler knows what that name means. Similarly, when we use a type parameter name in the function signature, we have to declare the type parameter name before we use it. To define the generic largest function, place type name declaration inside angle brackets between the name of the function and parameter list. Like this, we read this definition as the function largest is generic over some type t. This function has a parameter name list, which is a slice of values of type t. Largest function will return a reference to a value of the same type. Listing 10-5 shows the combined largest function definition using the generic data type in its signature. The listing also shows how we can call the function with either a slice of i32 values or a char values. Note that this code won't compile yet, but we will fix it later in this chapter. If we compile this code right now, we will get this error. The help text mentions partial odd, which is a trait, and we are going to talk about traits in the next section. For now, know that this error states that the body of the largest won't work for all possible types that t could be. Because we want to compare values of type in the body, we can only use types whose values can be ordered. To enable comparison, the standard library has the partial odd trait that you can implement on type. See appendix C for more on this trait. By following the help text suggestion, we restrict the types varied for t to only those that implements partial odd, and this example will compile because the standard library implements partial odd on both i32 and char. In struct definition, we can also define structs to use a generic type parameter in one or more fields using the uh, diamond syntax. Listing 10-6 defines a point t struct to hold x and y coordinate values of any type. The syntax for using generics in struct definition is similar to that used in function definition. First, we declare the name of the type parameter inside angle brackets just after the name of the struct. Then we use the generic type in the struct definition where we would otherwise specify concrete data types. Note that because we have only used one generic type to define point t, this definition says that the point t struct is generic over some type t, and the fields x and y are both that same type, whatever that type may be. If we create an instance of a point t that has values of different types as in listing 10-7, our code won't compile. In this example, when we assign the integer value 5 to x, we let the compiler know that the generic type t will be an integer for this instance of point t. Then we specify 4.0 for y, which we have defined to have the same type as x. We will get a type mismatch error like this. To define a point struct where x and y are both generics but could have different types, we can use multiple generic type parameter. For example, in listing 10-8, we change the definition of point to be generic over types t and u, where x is of type t and y is of type u. Not all instances of points shown are allowed. You can use as many generic type parameters in a definition as you want, but using more than a few makes your code hard to read. If you're finding you need lots of generic types in your code, it could indicate that your code needs restructuring into smaller pieces in enum definition. As we did with structs, we can define enums to hold generic data type in their variant. Let's take another look at the option t enum that the standard library provides, which we used in chapter 6. This definition should now makes more sense to you. As you can see, the option t enum is generic over type t and has two variants, some which holds one value of t and a none variant that doesn't hold any value. By using the option t enum, we can express the abstract concept of an optional value, and because option t is generic, we can use this abstraction no matter what the type of the optional value is. Enum can use multiple generic types as well. The definition of the result enum that we used in chapter 9 is one example. The result enum is generic over two types t and e and has two variants, okay, which holds a value of type t and error which holds a value of type e. This definition makes it convenient to use the result enum anywhere we have an operation that might succeed, return a value of some type t, or fail, return a value error of some type e. In fact, this is what we used to open a file in listing 9-3 where t was filled in with the type stdfs file, where the file was opened successfully, and e was filled in with the type stdio error, where there were problems opening the file. When you recognize situations in your code with multiple struct or enum definition that differ only in the types of the value they hold, you can avoid duplication by using generic type instead. In method definition, we can implement methods on structs and enum as we did in chapter 5 and use generic types in the definition to. Listing 10-9 shows the point struct we define in listing 10-6 with a method name x implemented on it. Implementing a method name x on the point t struct that will return a reference to the x field of type t. Here we have defined a method name x on point t that returns a reference to the data in the field x. Note that we have to declare t just after impl, so we can use the t to specify that we are implementing methods on the type point t. By declaring t as a generic type after impl, Rust can identify that the type in the angle bracket in point is a generic type rather than a concrete type. We could have chosen a different name for this generic parameter than the generic parameter declared in the struct definition, but using the same name is conventional. Methods written in an impl that declares the generic type will be defined on any instance of the type, no matter what concrete type ends up substituting for the generic type. We can also specify constraints on generic type when defining methods on the type. We could, for example, implement methods only on point f32 instance rather than on point t instance with any generic type in listing 10-10. We use the concrete type f32, meaning we don't declare any types after impl point f32 fn distance from origin, an impl block that only applies to a struct with a particular concrete type for the generic type parameter t. This code means that the point f32 will have a distance from origin method. Other instances of point t where t is not of type f32 will not have this method defined. This method measures how far our point is from the point at coordinate 0.00.0 and uses mathematical operations that are available only for floating point types. Generic type parameter in a struct definition aren't always the same as those you use in that same struct's method signature. Listing 10-level uses the generic type x1 and y1 for the point struct and x2 and y2 for the mix-up method signature. To make the example clearer, this method creates a new point instance within the x value from the self point of type x1 and y value from the passed in point of type y2. impl point fn mixin In main, we have defined a point that has an I32 for x with value 5 and an f64 for y with a value 10.4. The p2 variable is a point struct that has a string slice for x with value hello and a char for y with a value c. Calling mixup on p1 with the argument p2 gives us p3, which will have an I32 for x because x came from p1. The p3 variable will have a char for y because y key from p to the println macro will print p3 dot x equal to 5 and p3 dot y equal to c. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with impl and some are declared with the method definition. Here the generic parameter x1 and y1 are declared after impl because they go with the struct definition. The generic parameter x2 and y2 are declared after fn mixup because they are only relevant to the method performance of code using generic. You might be wondering whether there is runtime cost when using generic type parameter. The good news is that using generic type won't make your program run any slower than it would with concrete type. Rust accomplishes this by performing monomorphization of the code using generic at compile time. Monomorphization is the process of turning generic code into specific code by filling in the concrete type that are used when compiling. This process the compiler does the opposite of the steps we use to create the generic function. In listing 10-5, the compiler looks at all the places where generic code is called and generates code for the concrete type the generic code is called with. Let's look at how this works by using the standard libraries. Generic option t enum, let integer sum 5, let float sum of 5. When Rust compiles this code, it performs monomorphization. During that process, the compiler reads the value that have been used in option t instance. I identify two kinds of option t. One is i32, another is f64. As such, it expands the generic definition of option t into two definitions specialized to i32 and f64, thereby replacing the generic definition with a specific one. The monomorphized version of the code looks similar to the following. The compiler uses different names than what we are using here for illustration. The generic option t is replaced with the specific definition created by the compiler. Because Rust compiles generic code into code that specifies the type in each instance, we pay no runtime cost for using generic. When the code runs, it performs just as it would have if we had duplicated each definition by hand. The process of monomorphization makes Rust generic extremely efficient at runtime. So we will look traits in the next video. Thank you for watching. Bye.